Galaxies are vast systems of stars, gas, dust, and dark matter held together by gravity. They are the building blocks of the universe, containing billions to trillions of stars. Our Milky Way galaxy, for example, is home to over 100 billion stars. Galaxies come in various shapes and sizes, ranging from small dwarf galaxies with just a few million stars to giant elliptical galaxies with trillions of stars. The study of galaxies is crucial to understanding the cosmos and our place within it. Galaxies are not randomly scattered throughout the universe, but are organized into groups and clusters. These structures are interconnected by vast filaments of dark matter and gas, forming a cosmic web that spans the universe. The distribution of galaxies on these large scales reveals important clues about the underlying structure and evolution of the universe. One of the key features of galaxies is their spiral arms, which are regions of intense star formation and stellar activity. These arms wind outward from the galaxy's central bulge, where a supermassive black hole often resides. Spiral galaxies, such as the iconic Andromeda galaxy, exhibit beautiful spiral patterns that are a result of the rotation of stars and gas within the galaxy. In contrast, elliptical galaxies have a more rounded and elongated shape, lacking the distinct spiral arms of their counterparts. These galaxies are often composed of older stars and contain less gas and dust, leading to lower rates of star formation. Elliptical galaxies are thought to form through mergers of smaller galaxies, which disrupt the original structure and create a more spheroidal shape. Understanding the formation and evolution of galaxies is a complex and ongoing area of research in astrophysics. By studying the properties of galaxies at different cosmic epochs, scientists can piece together the history of the universe and unravel the processes that have shaped the cosmos we see today. Galaxies exhibit a wide range of structures, each with its unique characteristics and properties. One of the key components of galaxy structure is the central bulge, a dense region at the core of the galaxy that contains a high concentration of stars. The bulge can vary in size and shape, with some galaxies having a prominent bulge, while others have a more subtle one. Surrounding the bulge are the spiral arms, which extend outward in a spiral pattern. These arms are regions of active star formation, where young, hot stars are born from the gravitational collapse of gas and dust. The spiral arms are also home to massive star clusters and nebulae, adding to the visual richness of the galaxy. In addition to spiral galaxies, there are also elliptical galaxies, which lack distinct spiral arms and have a more rounded or elongated shape. Elliptical galaxies are primarily composed of older stars and contain little interstellar gas and dust, leading to lower rates of star formation. The structure of elliptical galaxies is often determined by their degree of flattening, ranging from nearly spherical to highly elongated. Another type of galaxy structure is the irregular galaxy, which lacks a defined shape or symmetry. Irregular galaxies are often the result of gravitational interactions with other galaxies, leading to distorted shapes and chaotic star formation patterns. These galaxies can exhibit a wide range of sizes and luminosities, making them a diverse and intriguing class of objects to study. The overall structure of a galaxy is also influenced by the presence of dark matter, a mysterious substance that does not emit, absorb, or reflect light. Dark matter exerts a gravitational pull on visible matter, shaping the distribution of stars and gas within the galaxy. By studying the motions of stars and gas in galaxies, astronomers can infer the presence of dark matter and map its distribution throughout the galaxy. Understanding the structure of galaxies is essential for unraveling their formation and evolution processes. By analyzing the distribution of stars, gas, and dark matter within galaxies, scientists can piece together the history of these cosmic structures and gain insights into the underlying physical processes that govern their behavior. Galaxies come in a variety of types, each with its unique characteristics and properties. Understanding the different types of galaxies is essential for unraveling the diversity and complexity of the universe. The three main types of galaxies are spiral galaxies, elliptical galaxies, and irregular galaxies. Spiral galaxies are characterized by their distinct spiral arms that wind outward from a central bulge. These arms are regions of active star formation, where young, hot stars are born from the gravitational collapse of gas and dust. Spiral galaxies often have a flattened disk shape with a prominent central bulge containing a high concentration of stars. The Milky Way, our own galaxy, is a prime example of a spiral galaxy, with its beautiful spiral arms and central bulge housing a supermassive black hole. Elliptical galaxies, on the other hand, lack the spiral arms of their counterparts and have a more rounded or elongated shape. These galaxies are primarily composed of older stars and contain little interstellar gas and dust, leading to lower rates of star formation. Elliptical galaxies are classified based on their degree of flattening, ranging from nearly spherical to highly elongated shapes. Some elliptical galaxies, known as giant ellipticals, can contain trillions of stars and dominate the centers of galaxy clusters. Irregular galaxies represent a diverse and chaotic category of galaxies that lack a defined shape or symmetry. These galaxies often result from gravitational interactions with other galaxies, leading to distorted shapes and irregular star formation patterns. Irregular galaxies can vary widely in size and luminosity, making them a fascinating class of objects to study. One subtype of irregular galaxies is the Magellanic Clouds, which are small, satellite galaxies of the Milky Way. These galaxies exhibit irregular shapes and are actively forming new stars, providing valuable insights into the processes of galaxy evolution. Another interesting type of galaxy is the lenticular galaxy, which combines features of both spiral and elliptical galaxies. Lenticular galaxies have a disc-like structure similar to spiral galaxies, but lack the prominent spiral arms. Instead, they have a smooth, featureless appearance like elliptical galaxies. Lenticular galaxies are often found in galaxy clusters and represent a transitional stage between spiral and elliptical galaxies. Understanding the different types of galaxies is crucial for piecing together the puzzle of cosmic evolution and unraveling the mysteries of the universe. Galaxies are not static entities but are constantly evolving over cosmic timescales. The formation processes of galaxies are complex and involve a combination of gravitational interactions, gas accretion, star formation, and feedback mechanisms. One of the primary mechanisms responsible for galaxy formation is hierarchical merging, where smaller galaxies merge together to form larger, more massive galaxies. This process is driven by the gravitational attraction between galaxies and is particularly common in galaxy clusters, where interactions are frequent. Through successive mergers, galaxies grow in size and mass, eventually forming the giant elliptical galaxies that dominate the centers of galaxy clusters. Another key aspect of galaxy formation is gas accretion, where galaxies accumulate gas from their surroundings to fuel star formation. Gas accretion is essential for replenishing the gas reservoirs within galaxies and sustaining ongoing star formation. The inflow of gas can be facilitated by interactions with neighboring galaxies, as well as by the cooling and condensation of hot gas in galaxy halos. Star formation is a fundamental process that shapes the evolution of galaxies and contributes to their overall structure and appearance. Stars form from the gravitational collapse of dense regions within interstellar clouds, where gas and dust condense to form protostars. These protostars undergo nuclear fusion in their cores, releasing energy and light into the surrounding environment. The birth of new stars enriches galaxies with heavy elements synthesized in stellar interiors, such as carbon, oxygen, and iron. Supernova explosions, which mark the end of massive stars' lives, also play a crucial role in enriching galaxies with heavy elements and driving galactic winds that can expel gas from galaxies. Feedback mechanisms, such as supernova explosions and active galactic nuclei, regulate the star formation rates within galaxies and influence their overall evolution. These mechanisms can heat or expel gas from galaxies, quenching star formation in some regions while promoting it in others. The interplay between feedback processes and star formation is a key factor in shaping the diversity of galaxy types observed in the universe. Understanding the formation processes of galaxies is essential for unraveling the origins of cosmic structures and the evolution of the universe. By studying the properties and dynamics of galaxies at different cosmic epochs, astronomers can piece together the history of galaxy formation and gain insights into the physical processes that govern the growth and evolution of these cosmic entities. Galaxy evolution is a fascinating journey through cosmic time, where galaxies transform and evolve in response to internal and external processes. One of the key drivers of galaxy evolution is mergers and interactions between galaxies. When galaxies collide, their gravitational forces distort their shapes, trigger intense bursts of star formation, and can ultimately lead to the formation of new, more massive galaxies. The Milky Way, for example, is believed to have undergone multiple mergers with smaller galaxies throughout its history, shaping its current structure and composition. Another important aspect of galaxy evolution is the role of supermassive black holes at the centers of galaxies. These black holes can accrete gas and dust, releasing vast amounts of energy in the form of active galactic nuclei, AGN. AGN feedback can regulate star formation rates within galaxies, heat or expel gas, and influence their overall evolution. The interplay between black holes and their host galaxies is a dynamic process that shapes the growth and evolution of both entities. Galaxies also evolve through secular processes, such as bar instabilities and spiral arm dynamics, which redistribute gas and stars within galaxies over long timescales. These processes can drive the formation of new structures and features within galaxies, contributing to their diversity and complexity. Studying galaxy evolution provides valuable insights into the history of the universe, the formation of cosmic structures, and the physical processes that govern the evolution of galaxies. Observational techniques play a crucial role in studying galaxies and unraveling their mysteries. Astronomers use a variety of tools and instruments to observe galaxies across different wavelengths of light, from radio waves to gamma rays. One of the most common techniques is optical astronomy, which involves observing galaxies in the visible light spectrum using telescopes equipped with sensitive detectors. By analyzing the colors and brightness of galaxies in optical light, astronomers can infer important properties such as stellar populations, star formation rates, and chemical compositions. In addition to optical observations, astronomers also use radio telescopes to study galaxies emitting radio waves, which provide insights into processes such as synchrotron radiation and active galactic nuclei. Another powerful observational technique is infrared astronomy, which allows astronomers to peer through the dust clouds that obscure visible light and observe the warm glow of dust-enshrouded star-forming regions. By combining observations from different wavelengths, astronomers can construct a more complete picture of galaxies and their evolution over cosmic time. Advanced technologies, such as adaptive optics and interferometry, have revolutionized observational astronomy by enhancing the resolution and sensitivity of telescopes, enabling astronomers to study galaxies in unprecedented detail. Observational techniques continue to push the boundaries of our understanding of galaxies, revealing new insights into their structures, dynamics, and formation processes. Recent research has uncovered fascinating insights into galaxy evolution. Studies have shown that galaxy mergers play a significant role in triggering star formation and shaping galaxy structures. Observations of distant galaxies have revealed a population of red nugget galaxies, compact and massive galaxies that formed early in the universe's history. Additionally, advancements in observational techniques, such as the use of gravitational lensing, have allowed astronomers to study galaxies with unprecedented detail. The discovery of ultra-diffuse galaxies, large galaxies with low surface brightness, has challenged our understanding of galaxy formation. These ongoing research efforts continue to expand our knowledge of galaxies and their evolution. The future of galaxy studies holds exciting prospects, with upcoming technologies like the James Webb Space Telescope promising to unveil new insights into the early universe and galaxy formation. Advancements in computational simulations will allow scientists to model complex interactions within galaxies with greater accuracy. Collaborative efforts, such as the Large Synoptic Survey Telescope, will survey the entire sky multiple times, providing a wealth of data for studying galaxy evolution. The integration of artificial intelligence and machine learning algorithms will revolutionize data analysis, enabling researchers to sift through vast datasets more efficiently. The future of galaxy studies is bright, offering a deeper understanding of the cosmos and our place within it.